All right. So our last talk for today is by Andrey, and he will be talking about coverage-guided USB fuzzing. So please give him a big applause.
Hi. Thank you all for coming. And this is a talk about USB fuzzing, as was just mentioned. And my name is Andrey. And I work at Google. I work on different kinds of tools for the Linux kernel that find bugs. And internally, my team is known as the dynamic tools team. And we have a bunch of tools for user space, and we have a bunch of tools for kernels. Some of them were mentioned, actually, earlier today. So there are like two parts to my team. The one that does user space, it is the part of team that made ASAN, TSAN, MSAN, and other kinds of bug detectors happen. And if you write C++ code, you probably know about them, or like if you find bugs in C++ code. The thing that was mentioned earlier today is called libfuzzer, which is kind of an in-process AFL, like it's a framework for fuzzing. And recently, there was also a thing that's called OSS-fuzz. And basically, the whole idea is that open source projects can submit their fuzzers to Google, and Google will run them on their fuzzing farms with hundreds of servers, which is quite efficient. And the part of the team that does kernel stuff, we also made a bunch of similar tools to ASAN, TSAN, and others for the kernel, which was called kernel ASAN, kernel MSAN. They are bug detectors. And the thing that we'll be talking about today is called Syzkaller, which is a coverage-guided grammar-based kernel fuzzer. OK, this is what we're going to cover today. And I'm going to give some introduction into what is Syzkaller and what is the USB protocol and how we're going to combine them together. At the end, we actually, the whole, like a small spoiler, the whole fuzzing is going to be happening in a VM, but we're actually going to launch some hardware reproducers, and we're going to crash actual kernels with that. Hopefully it works. OK, let's start with Syzkaller. So before Syzkaller, there was a fuzzer called Trinity. And the whole idea of fuzzing the kernel is basically just issue syscalls. Trinity did that. It even didn't set all of the arguments of syscall randomly. It knew whenever you need a file descriptor to pass in a file descriptor, or whenever you need a valid address, it would pass an address. The problem is that with Trinity, it was just randomly shooting syscalls. And even suppose you run Trinity for 10 hours and you trigger a bug. The problem is that you can't actually reproduce it, and the only thing that you have is a crash. Even if you start Trinity with the same initial seed, so you would issue the same syscalls, the problem is that the kernel is very indeterministic, so there's no guarantee that the same thing is going to happen again and you're going to trigger the same condition. And also, since it doesn't use coverage guidance or other kinds of guidance, it's kind of finds not very deep bugs. So this is where Syzkaller comes in. And well, the idea was basically we do the same thing as Trinity. We issue syscalls. But first of all, we want to collect coverage and kind of be coverage guided. And the second thing that we want to do is to be grammar-based, which is kind of the fuzzer has some structure awareness on which kind of structures you have to pass into different system calls. So there are some complicated ones. It's you pass a pointer to a struct which has pointers to other structures. And the fuzzer can generate those kind of things and do that. And initially it started as a fuzzer for the Linux kernel, but since then, people came and they added FreeBSD, OpenBSD, and other BSD support in there. It also kind of supports Fuchsia, which is a Google operating system, which is supposedly should be used on mobile devices at some point in the future. Yeah, it supports a bunch of different architectures, and well, you can actually fuzz on different kinds of target machines. So you can use QEMU and run your kernel inside QEMU and fuzz it there. You can use Google Cloud Engine. You can use actual Android phones or some of the boards. One of the coolest things that Syzkaller does is it can actually generate a C reproducer for a bug that it finds. It's quite useful. And as of now, we found a few thousand of bugs. There are a bunch of CVEs. The problem with CVEs is that the Linux kernel community doesn't really care about CVEs, because, I mean, usually the kernel developers, they fix bugs, and they care about the bugs. But they don't really care about going, requesting CVE, and doing all this process of like disclosure and stuff. And that's for security people, I guess. But it finds very interesting bugs. I fuzzed the kernel for, I mean, I was working on Syzkaller for more than a year now, and like more than 2 years, I guess. And I found some very interesting bugs for which there are public exploits. And okay, so how does Syzkaller work? As I mentioned, there are like 2 parts to it. The first part is we want coverage guidance, right? And the idea is that we basically do the same thing that libfuzzer or AFL does. So there is a GCC and clank path. Like one of the most important things that for the kernel we actually have the source. So it's easy to use compiler instrumentation to collect the coverage. And for GCC and clank, we have some compiler passes that just insert callbacks into every basic block when they compile the kernel. Then we have a kernel module that would collect PCs that come, or like how do you call it, like the current REP value basically from whenever this callback is called. And it would expose it to user space. One very important thing is that we collect coverage per task or per kernel thread. And if you collect coverage for the whole kernel while you fuzz it, there's like a lot of noise in there. And the idea is you collect coverage only for the thread that actually issues syscalls and does the fuzzing. And the second part to Syzkaller is the structure awareness. So there is a special language to describe different syscalls that Syzkaller understands. Here's a small snippet. It's quite self-explanatory. We describe like open, read, and close syscalls. And Syzkaller knows how to handle some. It has like some embedded types. For example, here file name is the type, and Syzkaller would know that whenever it issues an open syscall, the first argument should be a file name. It has support for flags. It has support for pointers, structures, unions, whatever else. And one of the also interesting properties of it is that, so here we can see that open syscall returns a file descriptor. It's like at the very end there's FD. It means like a return value. It's kind of like Go style of defining stuff. And Syzkaller would know that FD is what we call a resource, and they're like syscalls that generate resources. For example, open generates a file descriptor, and then you're supposed to pass this file descriptor to other syscalls. And this is how Syzkaller kind of figures out how to connect different syscalls between each other, right? So it would connect open and read, for example. And we use those descriptions, and those descriptions are actually manually written by us. I mean, my team are not really kernel experts. We covered some part of the kernel with those descriptions, but there are like some places to improve. Those descriptions are used to generate programs, which are, well, a program is just a sequence of syscalls. We use like also a different notation for this kind of stuff. Here's a small program that basically just opens a file and reads it. So the first syscall is mmap. We just mmap some memory to store the file name. Then we open the file with the name file0, and the actual string that holds the file name is stored in our mmap memory. Then we read 42 bytes from it, and then we close it. And Syzkaller has support for generating random programs like that and mutating them, so like changing syscall parameters, changing the order of syscalls, inserting new syscalls, removing syscalls, and so on. And the algorithm of fuzzing is quite usual. I mean, it's the same for every kind of like generation-based fuzzer. So you maintain a corpus of programs, and on each step you either generate a new program or you mutate one of the existing ones. You execute it, you collect coverage, and if there's any new coverage, you just add it back to the corpus. If there's not, you just throw it away, and you repeat it until you're done. Okay, so when we started doing that, ideally what we would want from a fuzzer is that fuzzer is some like magic box, and you fit resources into the fuzzer. So resources here means CPU time or RAM or whatever else. And the fuzzer would just like spew out proof of concept for you, right? But in reality, it's all a bit different because you need to do a lot of stuff manually. You need to like launch VMs, you need to copy the fuzzer binary and start it, you need to monitor the console output and actually parse crashes from there. And with Linux, it's extremely difficult. And so there's like a bunch of stuff that you need to spend a lot of time on. And this is what we wanted to address when we were building Syzkaller. And Syzkaller tries to do that up to some degree. This is like high-level overview of how it works. We have a main binary which is called sysmanager. And sysmanager just creates, well, basically it does all of that stuff that I just listed for you. So it can create VMs, it copies the fuzzer binary in there, it basically tells the fuzzer binary what to do, so the fuzzer would fuzz stuff. It would monitor the output from VMs, it would collect crashes, it would try to reproduce the bugs, and do a lot of stuff like this. And a little bit more detailed. So from this part, I mean, the sysmanager part we saw on the previous slide. Here we have a test machine, and inside the test machine we actually have two binaries. And the first one is sysfuzzer. It's basically kind of like an... Oh, let me start with the other part. The part that actually issues syscalls and collects coverage is called sysexecutor, and it's written in C. It's, 2,000 lines of C code, but the idea is basically sysmanager through sysfuzzer passes the programs sysexecutor should execute. Sysexecutor executes them, collects coverage, and gives the coverage back. And the part that actually decides whether the program generated some new coverage is called sysfuzzer. And sysfuzzer would reply, would return all of the new interesting programs back to sysmanager. Here we can also see that sysmanager actually collects console output from the test machine. So if we use QEMU, we use the serial console from QEMU. If we use GCEs, we also, Google Cloud Engine, there is also a serial console that allows you to kind of like dump stuff that's happening. Okay, so there is even like further automation. There are two tools that are quite useful. The first one is called SysCI, and the idea is that if you want to fuzz like a bunch of kernels and a bunch of different branches, and you want to continuously keep pulling in new updates for the kernels and continuously build them, SysCI does it for you. So you just would update the kernel, update the syscaller, and restart the manager. We also have a way to exchange corpuses between different sysmanagers, and this is what we use syshub for. The idea is that you can, for example, set up one sysmanager that fuzzes one kernel and another sysmanager that fuzzes another branch of this kernel. And some of them might happen to generate some interesting program. And with syshub, you can actually make them, exchange them. But I'd say the biggest thing in terms of automation, especially bug reporting automation, is called Sysbot. And Sysbot is actually I'd say it's a service. The idea is that we have a bunch of upstream kernels, some of the development kernel branches. We have sysmanagers for them running on GCEs, and we have a magic Sysbot machine which collects the crashes from those kernel and just reports them to kernel developers on mailing lists or whichever way they would prefer. So if you want to check it out, you can go to this website. It's basically a dashboard for Sysbot. I'm actually going to show it to you. So whenever you go to it, give me a second. Okay, this is what we're interested in. The dashboard has a few kernels besides the Linux kernel, because we also have support for other kernels. And this is the bug stats for the Linux kernel. So far, Sysbot reported thousands of bugs that got fixed. And at this point, we actually have 500 bugs that were reported but not fixed yet by Syzkaller or by the kernel developers. And here, it's quite cool that you can actually go into some of the bugs. And if you open some entry for the bug, it's going to tell you some stats about the bug report. And it's going to tell you basically just the stack of the kernel crash and stuff like that. But I'd say the most interesting part is that you can actually see reproducers here. So here's the link for syzrepro and crepro. Syzrepro is just the Syzkaller program that triggered this crash. And the idea is you can just take this program, you can just build the kernel, it crashed, you can copy this program into the kernel, execute it, and it would crash the kernel. I mean, the idea is to make it easy for upstream kernel developers to fix stuff, so just provide reproducers. To execute Syzkaller programs, you need a special tool, which is called sysexecproc, but just for your convenience, Syzkaller also generates a C program that is, well, if you look at this sys program, it says like openadd, ptmx, stuff like that. And this is what the C program actually says. So it also does openadd, it set up a bunch of structures or arguments for the ioctl, and it calls the ioctl. Okay. Let's talk a bit about USB. So I'm not going to go into details about the USB protocol, and if you're interested in USB, I found the article that I linked at the end very good. I mean, it only covers USB 2, but it's very good at explaining stuff. I will mention only the most important things. So first of all, with USB, so we all know what USB is, right? You have some USB device, you plug it into a host, and it starts magically working, right? The protocol between the host and the USB device is message-based. I mean, we're not going to go deep into this, but the most important thing is when you plug in a USB device, all the communication is initiated by the host. So when you plug in a device, a host would send a request to the device, and the device should reply, right? And I mean, this process happens throughout the whole time the device is connected. And how often the queries are and what exactly the host asks the device, it depends on the device, depends on the host, on a lot of stuff. When you plug in the device into the host, there is this process which is called enumeration. And the idea is that host is trying to figure out which driver should it use for this particular device. It works like that. So the device, when you plug it in, the host asks, like, what are you? And the device provides some very basic descriptor on what it is. And I'll show you it a bit later. And this descriptor has a bunch of IDs, and the host uses those IDs to select a driver it should load. If it doesn't have a driver, it just rejects the device. When the enumeration completes, host gives away the control over the device to the driver. Okay, I'm going to show you a little bit of stuff. So there is a Linux tool which is called LSUSB, right? And it just shows you the USB devices that are connected to your host. You can actually say it -v, and it's gonna dump all of the descriptors. Give me a second. So here, it's gonna dump all of the descriptors that the connected USB devices have. This is actually the thing that I mentioned. So whenever you plug in the device, this is what we're looking at is an optical mouse. I have it like plugged in right here. This is a Logitech mouse, and when you plug in this mouse, the host would ask you for this descriptor, and the device would reply. The descriptor has some interesting IDs, ID vendor and ID product, and the host will use these IDs to figure out which driver to load. These are not the only things that are used to figure out the driver. So for example, the thing that's called device class. Here it says device interface level. So USB descriptors are complicated, and I'm not going to explain it, but here's interface class, human interface device. And the idea is that the kernel has a bunch of standard drivers for some USB classes, for some standard USB device classes. And the kernel might load a specific driver for this specific device based on the vendor and product IDs if the kernel has it. But if it doesn't, it would just see that it's a generic HID device and just load the generic HID driver and let it handle it. And here we can actually go to Wireshark and see how this process happens. So this is the part where the communication starts. And yeah. So here we can see that hosts issues a request to device number 20 on the first USB bus. And it's a get descriptor request device. So the host asks for the device descriptor. and the device replies. And we can actually see that this is the Wireshark capture that I took when I plugged in the mouse that I just showed you. And we can actually see that it just sends the very same descriptor we saw in the LS USB just now. Right. And there is like this whole process of communication. So the host requests one descriptor, then device replies, host requests something else, device replies, and so on and so on. So this process is what is called enumeration. And after enumeration is done, the host issues set configuration request. Okay, so this is what we're actually going to be fuzzing for the most part. So when the host requests a descriptor, we want to inject some random stuff. But we don't want to do it stupidly. We want to inject some structure, to use some structure awareness to do that. Right. Let's go back here. Okay, yeah, just a bit more. This is a picture of how the Linux USB subsystem looks from the inside. I'd say this is easier to read from the bottom to top. So we have three layers in this picture. We have the hardware layer, we have the kernel layer, and we have the user space layer. And on the hardware layer, we have USB port. That's where we plug in our device, right? The USB port is connected to a piece of hardware that's called USB host controller. And, well, I have Raspberry Pi here, and on the Raspberry Pi, this hardware piece is just embedded into the system on chip that we have on Raspberry Pi. For this USB host controller, we have a driver in the kernel, and it's called USB host controller driver. The driver plugs the USB controller into a middle layer, which is called USB core. And the whole idea is to abstract away the different kinds of host controller drivers that you might have. Right. The USB core knows, so USB host controller drivers communicates with the USB core with some standard API, and it basically passes the packets it receives from the device, messages it receives from the device to the USB core. Based on those messages, USB core figures out like what to do with the device, what to reply, and whether it should load any drivers. If it loads any drivers, so here I have USB HID, USB My Storage, and there might be more. Those drivers expose themselves to the user space somehow. So, for example, when you plug in a webcam, the webcam gets exposed as like /dev/video0 or whatever. And this is like an overview of how the host subsystem of the USB works. Okay, what were the previous approaching on fuzzing this stuff? I'd say there are like two. I mean, there are two ideas before. The first one is just use some hardware. And there is this thing that's called phase dancer. I have one of the older boards right here. And basically just a piece of hardware that allows you to emulate USB devices. So it actually has some Python framework written for it. And you connect this part into your host machine that you control, and this part into the machine that you're trying to attack. And you can actually drive this device with Python, and you can basically send USB messages to it, and they're going to get passed to the other end, to the machine you're trying to attack. And the other idea that I saw is using some kind of hypervisor to inject USB packets into the kernel to connect USB devices to the guest kernel. So, I mean, I saw a bunch of articles. There is one tool that is actually published on GitHub, and you can just run it and test it. It's called vUSBF, and it uses the thing that's called USB reader protocol inside QEMU. So QEMU just out of the box supports passing USB messages to the internal kernel and connecting USB devices. Okay, let's go to the main part. So what we want to do is to try to fuzz the USB with Syzkaller. And this is the picture that initially were in our minds when the Syzkaller was developed. So you have the kernel. And the kernel, I mean, it's kind of like any other program. It just accepts user input, and this user input can trigger bugs. For the kernel, the user input that's usually mentioned are syscalls, and you issue them from user space. But if you think about it, the kernel actually has a lot more different kinds of inputs. For example, you have network packets that come over your Ethernet port, and you have USB traffic, which, I mean, you plug in a USB device and the kernel should handle that. And the goal is we want to fuzz the USB stack externally. So we want to fuzz the USB core part and we want to fuzz the drivers part. And there are kind of like two things that we would want ideally. The first one is we would want coverage to be collected from USB so our fuzzing is coverage guided. The problem is that USB is actually handled in a background thread in the kernel. But currently, the way that Kcoff, which is the thing that collects kernel coverage, works is just collects it from the current thread. So we need to somehow implement that asynchronous coverage collection. The second part is that ideally we would want this on Sysbot. And I mean, the idea is that we don't really want to report bugs manually, and it's really nice to take care of the infrastructure. I mean, to take advantage of the infrastructure we already have for doing that. The problem is that on Sysbot runs on GCE, which is Google Cloud Engine, and it's like we can't actually use some other kind of hypervisor because we'd need to use GCE. In theory, we could launch a QEMU and instance inside of GCE and launch a guest kernel inside QEMU and do stuff like that, but it sounds quite difficult. So it would be nice to have some kind of way to do it within the kernel, right? Let's address the first part. The first part is that we want to collect coverage from USB. And I mean, it's not really that difficult. You just need to implement this background coverage collection in the kernel. So you need to modify the kernel Kcoff. And well, the idea is that we don't want to collect coverage from all the threads in the system, but we want to somehow point out the threads that we want to handle. And the way I did it is just add annotations. So I'm going to show it a bit later. The patches that, I mean, there are links here. I'm going to share the slides later. You can check out the patches as well. And from the point of view of usage, so before these patches, you would use Kcoff like this. And the idea is that you open a Kcoff file, you mmap a buffer where you would want to collect the coverage, and you issue a Kcoff enable ioctl. And at this point, the coverage from the current thread is going to be collected into this buffer. But after this patch, you can actually do this. So the top snippet is actually kernel code, and the bottom snippet is user space code. Hub event is the function that inside the kernel handles different events that happens on USB cup. So in particular, it handles all of the USB enumeration process. And the idea is that you add annotations to this function and use some unique ID. And I mean, then you use this unique ID to pass it to an ioctl that you call from user space. And that's basically the whole idea. So after you issue this Kcoff remote enable ioctl, the coverage from this background thread is going to be collected into this buffer that you mapped. So yeah. Okay, now to the second part, which is much more non-obvious, I'd say. How do we inject USB packets? So Syzkaller can actually now inject network packets, and there is an interface which is called TuneTab. There is a device which is /dev/tune, and if you configure it properly, whenever you write some data into this device, this data would go through the same parsing path as an external packet. So it would go through the whole TCP/IP stack, and you can actually find externally triggerable bugs over the network like this. The question is, can we do something similar for USB? So it's tricky for, I'd say the reason it is tricky is because USB communication is initiated by host. So network communication is initiated by anybody. So you can just kind of send data to some device and it gets parsed and handled by the kernel. But you can't actually do it with the USB easily this way, because you're supposed to have some state inside the kernel that actually expects you to send data right now. So yeah, I was reading and trying to figure out, I was reading a lot of documentation trying to figure out how to do stuff like this. And what I stumbled upon is the thing that's called gadget USB subsystem. The whole idea is that if you have a Linux device, like some Linux boards usually, you can actually turn them into a USB gadget. And there is a whole subsystem that's called gadget subsystem for that. This subsystem provides a few interfaces to the user space. I'm not sure which one is the most frequently heard about, but I mean, I like to think about GadgetFS because it's the simplest one, I'd say. The idea is that the kernel provides an interface to the user space to actually implement USB devices in the user space. So let's take a look at this picture, because I mean, it's much easier to see this way. So the idea is that here on the right, let's read it from top to bottom. So we have a thing that's called user space device app. And this is actually the user space app that's going to implement all of the logic of our USB device. And we will use GadgetFS interface for that. We can actually, instead of using GadgetFS, we can implement the whole thing in the kernel and use our kernel, some custom kernel module. It's like one of the two options that you can use. It's easier to handle stuff in user space, so that's, I mean, let's say we walk the left path and we walk down. So there is this thing that's called USB Gadget Core, and basically it's the same thing that we saw before. Like, it's kind of like intermediate layers that would provide API for different kinds of drivers. And so, I mean, you have different USB device controller drivers. USB device controller is same thing, that similar thing that a USB host controller is. It just instead of being a host, it's being a device. It can be a device. So USB Gadget Core provides some APIs for different drivers to register themselves. And yeah, this works like this. So if you have a USB device controller and we have some USB port, we can just plug in this port into a USB host and then use GadgetFS to implement some device. So let's put the other part of the picture back in. So right now on the left we have the host USB subsystem, and on the right we have the gadget USB subsystem. And this is what we're trying to attack. So we want to attack the USB core part, and we want to attack the drivers. And we want to do it like from below, externally. And the question is, can we somehow do it so we don't need any hardware? And actually, there is a magical config that's, I mean, it took me some time to figure out what it is and to find out how it works. But it's just a config that implements two virtual drivers, the one for host controller and the one for device controller, and just connects them within the kernel. So at this point, what you have is this all happens within one VM or within the same device. And you don't need any hardware. So you can actually write a user space app that through GadgetFS or through something else would emulate a USB device. And via the dummy drivers, it would just be connected back to the same kernel. So you're kind of like connecting USB devices from the user space to the kernel this user space is running on. Okay. So initially, I was looking at GadgetFS, and I was trying to fuzz stuff through GadgetFS. But the problem with GadgetFS is that, first of all, it has some sanity checks on the descriptors that you pass. So, I mean, ideally, we would want to pass as much corrupted stuff as possible, right? And second thing is that GadgetFS has some, I mean, it handles part of the communication logic. So it doesn't provide you to reply to every kind of packet, right? It handles some of them by themselves. So at this point, I thought it's a good idea to write my own kernel fuzzer module, as I call it. I mean, if it's going to get upstreamed at any point, it might be upstreamed as a part of GadgetFS, but right now it's just a separate module. And, well, the idea is that let's take a look at the picture. It actually has this module in. So this is actually the whole idea of the fuzzing approach. So in user space, we have the sysexecproc application that we saw before. We have my USB fuzzer kernel module that provides a interface kind of like GadgetFS to the user space. And on the other side, it's plugged into USB Gadget Core. All right. And then we use the dummy drivers and connect to the USB core subsystem. So yeah, that's the whole idea. The one thing that we actually thought about after that is that you can actually kind of test devices from both ends at this point. So you can emulate some USB device and connect it to the kernel. You make I mean, if you emulate a USB camera, it's going to get exposed to zero space as a device in /dev, right? And you can issue ioctls on this device. So it's kind of like testing from both ends. It's not implemented yet, just an idea. Okay. So for handling this stuff, I had to write some USB descriptions. And let me actually show them. They are in Syzkaller format. So they look like this. I've described some of the standard descriptor structures that they have in USB. And this is like the most important one, device descriptor. It has a bunch of stuff in it. And they're like, I'd say I described like 30 different structures. And I've also added, it's kind of like fake syscall. So the idea is that sometimes you don't have an actual syscall to execute some complex thing that you want to do. So instead, you use basically just a function that from the point of view of Syzkaller, from the point of view of generating programs, it's a syscall, but it just implemented as a function in C. Yeah, the part that I just shown you are the different kinds of device descriptors. There's also the second part, which are USB device IDs. And, well, what I did, I ran the kernel, I ran the Ubuntu kernel, if I remember correctly, or I like some equal kernel, and I just, in runtime, kind of got all of the IDs for different drivers that this kernel uses. And I just, like, with a script, converting them into Syzkaller descriptions. And it helps to, if you guess IDs randomly, it does really work good. And even coverage does really help with that. So just having a list of different IDs helps a lot. And this is what this fake syscall would look like. And it's quite simple. The argument that it has is actually generated based on those structures that I described. And it would just open a USB fuzzer. And here it's actually missing a step. I forgot it. So the idea is that first you need to, let me fix it. So what you want to do is you would actually want to have some USB device, right? And what you want to do is first like emulate device, or like connect device, I'd say better. Connect device, FD, USB device. Yeah, this looks better. So you connect a device that is based on those descriptions that you got passed, and then you wait for USB events. And whenever you have some event, some message you're supposed to reply to, you just get the reply from the description that you got passed. Okay, this is a demo for USB fuzzing in progress. So I'm gonna I have a dashboard cached, and so whenever you launch Sysmanager, you would get presented with something like this. So I can actually start it. It's going to take... OK, let me just show it. I can show the process later. And so the idea is that you start it. It's going to show you, when it's actually running, it's going to show you uptime. It's going to show you like corpus that you have, some coverage, and so on. And after running this whole thing and implementing it for like a week, I got a bunch of crashes. I mean, this is after I reported some of the bugs. So I mean, this is a decent amount, I'd say. Some of them are actually quite interesting. So for example, you have some use after few writes in there. Or you have some stuff like, where was it? Invalid free is basically double free most of the time. So like some decent memory corruptions you can actually trigger over USB. So yeah, and whenever you open some of these reports, and this is a report I'm going to actually show later, this is like some null pointer dereference in a SMS USB driver, whatever that is. And you can see the reproducer for this bug. It's very small. Basically, what you need to do, you just need to connect a device with some particular descriptor, and the kernel crashes. So, I mean, it's not really that deep. Oh, yeah. OK, yeah. The bug that I just mentioned, we can actually try to run it in a VM. I mean, try to reproduce it. So what I have here on the left is I have QEMU, which is right now booting. It has my USB fuzzer module inside, right? And I have the exact same reproducer I just showed you, like the one that's in SMS USB. What I'm going to do is I'm going to copy it to the VM, and I'm just going to run it. And let's see what happens. So to execute Syzkaller programs, you use a tool which is called sysexecproc. And I'm just going to pass it a bunch of flags. And I'm just going to specify this log file, right? OK. So here we have the same null. Where is it? So here it's at like connecting SMS USB, blah, blah, blah. Null pointer dereference, and here's the stack. So right now we reproduce this bug in a VM through the USB fuzzer module, and we had the dummy drivers loaded in there. OK, that's not all. Let's keep going. We have some time. OK, these are the results that I got, and I reported manually around 80 bugs in different subsystems. I'd say half of them got fixed, half of them got ignored. Yeah, and 5 of the bugs were in the USB core subsystem, which is kind of cool because, well, I mean, some of the devices, some of the boards or some of the kernels, they don't really have a lot of drivers that you can attack, but they also have the USB core subsystem. And if there are bugs in the core subsystems, like always triggerable, right? Even that you don't have any drivers. I have like a bunch of more that are not yet reported, but what we want to do is we want to integrate this into Sysbot and make Sysbot like report all of the bugs. And the funny part is that like while I was fuzzing this stuff, I found 12 bugs in the gadget subsystem because I was like stressing it. And I mean, it was my target, it was my tool, but it still crashed. So the limitation that we have is that it supports only Linux, right? Because I mean, you have the dummy stuff, and the whole approach works only on Linux. There are a little more limitations because the dummy drivers, they don't support what is called isochronous transfers, and those are the kinds of transfers that your webcam would make, that it was pass in video feed through the USB. It kind of like, sorry, it kind of limits the amount of stuff you can fuzz. Like some, also, it doesn't really handle some of the low-level USB requests. So what we want to do in the future, first of all, mostly so far we've been fuzzing the enumeration process. We want to fuzz also the subsequent communication. So we want to fuzz actually the packet that the webcam would pass as its video feed, right? We want to upstream all of the stuff that we have to the kernel. I mean, it might not be upstreamed in the way it looks like right now, but I mean, I'm going to send the patches to the upstream developers, and I'll see what they say. And I mean, the whole idea is to also try to fuzz other protocols besides USB. So you have like Wi-Fi, you have NFC, you have Bluetooth and stuff like that, and the kernel also handles that. OK, this is the cool part, because this is about generating hardware reproducers for the bug that we found. And let's take a look what we just did with the dummy interface. This is the demo that I just showed when we ran the reproducer inside the VM. And so, I mean, it looks kind of the same. You have sysexecproc, you have fuzzer module, gadget core, dummy driver, USB core. Let's actually look at, so what I have here, the board that I have here is called Raspberry Pi Zero, right? And Raspberry Pi Zero actually has a USB device controller inside of it. It's called DWC2. And this is the kind of like thing you would normally use Raspberry Pi for. So there are like a bunch of tutorials online on how you can emulate a keyboard on Raspberry Pi Zero. So you can like use GadgetFS and write the keyboard as a user space app, or there are some standard modules that would allow you to do it inside the kernel, like a ghit module that you can just load, and it's going to be a keyboard. OK, so let's do this. Let's take Raspberry Pi Zero, and instead of gadgetfs and kernel device module, we're going to load our USB fuzzer kernel module. And at this point, we can actually use our sysexecproc tool, because it uses the same interface. And we also have some USB host, and we can actually plug the Raspberry Pi Zero into a host. And this is the whole idea. You can just run the same reproducer via Raspberry Pi connected to a host. OK, let's try to show the demo. Give me a second. So what I have here is I have a camera that's set up to capture my laptop screen. And so yeah, and right here, I'm going to try to show it via the camera. I have a Raspberry Pi that's just connected to my laptop over a USB wire right here. Right. I hope you can see it. So at this point, we're going to wait for it to boot. So yeah, and Raspberry Pi Zero, it actually exposes UART interface through some of the pins, so you can just hook up a USB serial adapter and basically just get a shell on the Raspberry Pi Zero, like through UART. And actually, at this point, we can also see that the laptop actually detected that it has some device connected to it, but it can't receive any descriptors because our device just does reply. OK, we have a shell. So let's insert the module that we have to implement, to provide the interface for zero space. And now we can just run one of the reproducers. So I'm going to run the same SMS USB stuff. OK, let's see what happens. So what happened right now is that, I'm not sure if you saw, but we got a bunch of new lines on the screen of our computer. And the bug didn't trigger. There is a reason for why that didn't happen. And the reason is that it actually didn't go all the way down, I think. Or maybe it did. OK, the reason is that the SMS USB module wasn't actually loaded. But right now it says like USB core, and our reproducer, right now I just have like a hard-coded timeout for 1 second, and it just wasn't fast enough because the USB device disconnected before the module loaded. And this is actually what you have to take care of if you fuzz USB on real devices, because for modules, for drivers that are not loaded, it will take them longer to be loaded and initialized than for the modules that are already in there. So let's try it the second time. Boom. So right now we got so yeah, what we got here is we reproduce this bug over Raspberry Pi, right, on a real hardware. The kernel, so when Linux kernel crashes, sometimes it does really crash. And here we actually just crashed the background thread that handles the USB devices. And it's not really graphic when the Linux kernel crashes, because you either get a freeze or it's just like your laptop turns off or something like this happens, right? OK. Give me a second. OK, we have 6 minutes. We should be good. So some bonus. At this point, we can do something else. So yeah, after we fuzzed the Linux kernel, we collected some coverage, and we got a corpus of USB devices. And we actually have a way to execute those kind of like devices or programs via Raspberry Pi. So let's just connect it to Windows host and try to run all of the USB programs that we have. And the cool thing that I also wanted to do here is to get rid of all the wires, because right now, I have like a bunch of stuff in there, so you have to plug in stuff, and I mean, you have all these wires connecting stuff. The idea is very simple. Let's take not the $5 Raspberry Pi, but the $10 Raspberry Pi, and it has Wi-Fi on board. And we can set up a Wi-Fi hotspot, and we can just SSH to it, right? And what I also found very nice is that there is this thing that's called Zero Stem, and it's kind of like a small PCB you can just solder onto your Raspberry Pi Zero. And it just turns it kind of like a flash drive, a little bit bigger, but yeah. Okay, let's try to do this. Give me a second. Okay, here I have a laptop with Windows 10. And what I have plugged in here is the same thing that I just shown you. It's a Raspberry Pi that is with Zero Stem, and there are like no wires, it's just plugged in. Okay, each should have set up a Wi-Fi hotspot. Oops. Don't see it yet. I think I did. Maybe I'll need to move it a bit closer, I'm not sure. Oh yeah, perfect. That's the one. For some reason, when you follow the default tutorial to connect over Wi-Fi to Raspberry Pi to set up a Wi-Fi hotspot, it doesn't connect from the first time. You need to keep retrying for a few times, and then it just works. I don't know why. I haven't figured that out. So, yeah, right. Here's the camera, and here's the SSH that we have into our board. Right, let me turn this a bit. Perfect. What we're gonna do, we're also gonna insert the module, and we're gonna do just the same stuff. We're gonna run a repro. And the driver, so I ran the whole corpus that I have, and I think I saw 2 crashes. I have one of them here, and I call it ftdibus.log. Let's try to run it and see what happens. So, okay, that was it. Thank you all for coming, and if you have any questions.
Hi, great talk. One question. You said that half of the bugs you found were ignored by the kernel upstream team. Do you know of a reason why they did that?
Yeah, I'd say, I mean, there are a few reasons. Sometimes bugs just get lost on the mailing list. That could be it. Another reason is that in Linux, there are a lot of drivers that are not actually maintained anymore by anybody. And I mean, you send an email to people who are like listed as maintainers of these drivers, but their like emails don't work anymore, for example, or they just don't reply to you because I mean they worked on this stuff 15 years ago and then don't anymore, so they don't care. And yeah, I'd say those are the 2 main reasons.
Thank you for your talk. So probably you haven't looked at exploiting bugs, but from your experience in fuzzing USB and your experience with USB, do you think USB bugs are easy to exploit? Because I mean, from the browser you have like scripting languages to exploit the bugs with help.
So I can reply to this question about Linux, right? Because I mostly work on Linux, and I'd say it's possible, but I can't say that it should be easy. So it depends on the bug. For the bugs that I've looked at mostly, I mean, if I wanted to exploit some of them, that would probably be some double free or some kind of memory corruption like that. And for that, you need to like shape heap and do this kind of stuff, which isn't really easy over USB, considering that the kernel is multi-threaded, and I mean, you kind of like limited in the amount of interaction you can have with it. It should be possible. I don't think it will be very reliable for this kind of bugs, but yeah. But I mean, if you have some very good bug get that gives you like arbitrary read-write, of course, I mean, yeah.
Thank you for the talk, Andrew. When you were talking about integrating sending of USB packets to inject them into the kernel, did you consider USB IP, or it was not suitable?
I looked at it, and I mean, I've looked at USB IP, and I've looked at thing that called VHCI, I think, but I mean, I don't think those are the same thing or very similar, but for some reason I ended up with this approach. I can't give you all the details. I'd say my feeling told me that it would be easier to do.
Because it has the client side, the device side, and the host side. So
yeah, I know.
Thank you.
Anybody else? If you have, please keep the hand open. So up.
Thank you. Very nice talk, and thank you for the shout out to Phase Dancer. If Travis were here, I'm sure he would be glad to hear it. How did you find the Raspberry Pi's USB controller? Phase Dancer used the Max 3421, which was not always compliant, but for example, it would send NACs continually so that you didn't have the timeouts as much. Did the Raspberry Pi controller, prove more amenable or more restrictive? Or?
So what I actually wanted to have is something very, very cheap, right? And I'd say this is the approach that I took. And this thing costs $5, and it has some device controller. And basically, that's why I took it. I mean, I've tried it. If it happened that it doesn't work, I would choose something else. But the whole idea is that I wanted something with Linux, and I wanted something cheap, and I wanted something with a USB device controller. That's
obviously it's good enough at passing raw. Obviously, it's good enough at passing raw messages. It's like a raw socket.
Yeah.
Back to the other question about, can we do this like the IP way with raw sockets? Is it more forgiving or less forgiving
then Phase Dancer.
of the malformed USB packets than the Phase Dancer?
I don't think any of them care. I mean, they just pass messages. So as far as I understand, Phase Dancer actually allows you more low-level control of the USB communication, because some parts of the communication is actually handled by the gadget subsystem. So they have some low-level requests that just are not passed to the higher layers. With Phase Dancer, you can actually fuzz those as well. But I mean, both things, they just pass messages. The thing that you mentioned about NACs, I'm not sure about that. So. Okay. Thank you.